Hey guys, I'm gonna go ahead and walk through this test review. I know that the dates are on here, but just go ahead and stick with it. It's the same test review that we've got in this course. Feel free to skip through as much as you want. I'm gonna start on page 1 and I'll continue to go through. Video's long, I know. Just fast forward and rewind, whatever you need to see. All right, starting on the first one, talking about you need to know the structure of what a hypothesis test is, why we do it, and what the potential outcomes are. I typed up a little answer here, and I think it does a pretty good job summarizing it. A hypothesis test consists of two statements, a null and alternative hypotheses. Those are the two statements. We typically start with creating the claim and the opposite of the claim, and then we write our null and alternative hypothesis. But hypothesis test is generally just those two statements. We run statistics on these two statements to be able to support or not support claims. Notice I didn't say fail. You're supporting or not supporting claims. Now, that sounds different than the outcomes of the hypothesis test. The outcomes are either reject or fail to reject the null hypothesis. That then has implications on the claim. And I can't make a statement that summarizes all of this in particular because it changes from problem to problem. And that's what's important here is all of this changes. The big things, the things that stay the same is you're going to have two statements, a null and alternative hypothesis. The statistics can be run on those statements to support or not support claims. And then we can only reject or fail to reject the null hypothesis. Got to make sure you got that down because that is the basics of hypothesis testing. The next question here is talking about what type of tail you're going to have, left, right, or two-tailed. All that's based on the alternative hypothesis. And you can see here I've identified that when the alternative hypothesis has a less than sign, it's going to be a left-tailed test. A right-tailed sign is going to be a greater than symbol. And then two-tailed is going to be the not equal to. So that's going to tell you directly exactly how and what type of tail test you've got. The next question I'm asking you to know is to be able to identify what a p-value actually means. And the p-value is a probability. I know there's lots of p's in the class, but this is a probability. And it's really saying is that your sample statistics are true representations of the entire population, given that the null hypothesis is true. Remember, we always assume that null hypothesis is true. So whether your null is talking about, the mean of some value being equal to 12, if you assume this is true, and then you get some data, some p-value, and you find out that your p-value in your situation is 0.01, that's a pretty low p-value that we're going to reject our null hypothesis, meaning that that this is probably not true. If we've got a p-value this low, then our assumed assumption is probably not true because the p-value is a probability. So if you've got a probability of 1%, so you're really saying the probability of 1% is saying that your sample is representative of the entire population. So there's a 1% chance that this sample that you're gathering represents the whole population. That's really, really low. So that's not going to happen very often. Okay, so the next questions are going to be talking about, the next question here is being able to identify critical values, test statistics, rejection region, fail to reject region on both the traditional and the p-value curves. That's going to show up on these problems. And we're just going to jump right in. So page number 2, question number 5. I've got a sample of 635 of my former students. 360 of them thought Math 101 was awesome. The rest of them just thought it was super cool. Test the claim that the population proportion of students who thought Math 101 was awesome is greater than 50%. Another way you could just reward it is test the claim that most students thought Math 101 was awesome. Use a 1% significance level. So you can solve this in multiple different ways. We are going to solve it without the stats button, and then we're going to check it using our calculators. Before I start solving it using the traditional method, I want to talk about why and what type of problem this is. I give it to you directly, but I'm not going to be this nice to you on the test. I'm not going to tell you directly that it's a per population proportion. You should be able to see with the first statement, the sample of 635 students, 360 of them thought math was awesome. That should be screaming in your mind proportion. When you've got a situation where you've got a total number of students in a sample and you've got a small selection of those, that is a proportion. That's a really, really good thing, and it's going to make things easier for us as we move forward. All right, now to solve this in the traditional method, whether I'm doing the traditional method or the p-value method, I'm going to set up the first few things the first way. The first one is to identify the claim. My claim is that the majority of my students thought the class was awesome. So I'm going to go ahead and just write out that my claim is going to be P is greater than 0.5 or the proportion of the population is going to be greater than 0.5, greater than 50% or more of the students. All right. I'm going to go ahead and write the opposite of the claim as well, because I want to make sure I've got every step written down here and to make sure it goes smoothly. The opposite of P is greater than 0.5 is going to be that P is less than or equal to 0.5. Next step is going to identify the null and alternative hypothesis. I'm going to go ahead and do this in a different color here. So my null hypothesis is going to be the one that always has the equal sign. So my null is going to be P is less than or equal to 0.5. Remember, you could also write this as just that P is equal to 0.5. It's kind of a worst case scenario. This is the way that the book will write it for the most part, with just the equal sign. I will accept either solution. The alternative hypothesis in this case will be P is greater than 0.5. Next thing that I would like to do is I want to go ahead and identify where my claim matches up. This is going to make things much easier later. If my claim is attached to my alternative, I know that keyword is support. The last thing I really need to do before I start working on the critical values and the traditional method is just identify the two last things we need to do before we can start solving with this traditional and p-value. First one, we've got to identify the significance level. And then remember, we denote that with the alpha, so we've got a 0.01 significance level. And then the last thing we've got to do is we've got to identify that test statistic. We're going to do that in orange here. In the test statistic, because I've got a proportion, I know the equation to calculate the test statistic is going to be p hat minus p all over the square root of pq multiplied by the square root of n. Now, I've seen that written out a different way. Remember, we've seen that written out where you've got p hat minus p over the square root of pq over the square root of n. It's the exact same thing. Both of these formulas calculate the exact same thing. I just like seeing it with the full version with that times square root of n better. I think that does a better job for the calculations. So before I can calculate the p hat and the test statistic, is I've got to identify what my values are. So I got to look through the problem, and I've got 635 of my former students. So that is going to be my sample size. So that is my n. So my n is equal to 635. I've also got that 360 of those liked the class. So that's going to be my x, and that's going to be 360. My p hat, to calculate p hat, it hasn't changed from the very beginning of the course. It's just x over n, the number of successes out of the total of the population. In this case, that becomes 360 over 635. And when I type that in the calculator, I get a nice little decimal number that I'm going to estimate to be 567. I'm going to estimate it at 0.567. All right, now I just got to plug in what I've got into my test statistics formula. And I'm going to go ahead and write that out. 0.567 minus 0.5. Now, I know a lot of you guys are thinking, well, how in the world did he get that 0.5? Let's talk about that in just a second. Here's my p and my q in the denominator of my fraction. I know that my p is 0.5, my q is 0.5, and I'm going to multiply that by the square root of 635 for that n. So I think that some of you are saying, well, how in the world did he get this 0.5, this 0.5, and this 0.5? Well, let me come back and let me color code one of those. There we go. So the green 0.5 and the purple 0.5. Hopefully you're seeing that the green 0.5 is just valued equal to 0.5 from my formula here. And hopefully you can see where I got that. So this is my green and then my purple. Before I show you where I got the green and the purple from, let me remind you that once you've got one of those values, so let's say once you've got the value of p, you know the value of q immediately, because remind you, p plus q equals 1. All right, so that's something, if you know one of those, you automatically know the other one, right? That's a little reminder. Now, the other thing is that how in the world did I get that? And I've got that from, I've been saying in class that you get it from your null hypothesis, but that's actually incorrect. You get it from your null hypothesis. Where I got that p is equal to 0.5, it's right here. That is where I got that from. The null hypothesis is telling me p equals 0.5. That's what I'm giving you that value. It's coming directly from my null hypothesis. Now, you can also see that that's coming from my opposite of the claim, but that's not really what matters. What really matters is right here is where I'm saying, okay, p is equal to 0.5. I'm assuming that this is true. So that is going to be 100% true. It's going to show up in my null, and it's going to show up in my test statistic for formula. So when I'm ready to type this into the calculator, I'm going to do it step by step. I'm going to get a numerator that is equal to 0.067 over 0.5 multiplied by the square root of 635. Typing that into the calculator the one last time, I end up getting a value 3.377. So that is your test statistic. That should tell you quite a bit. And I'm not telling you have to have a conclusion done by now at all, but you should see where this is going. Now, going to the next step. I'm going to start with traditional method. And remember, with traditional method, you've got to use rejection region as well as your critical values. So I'm going to start with my alpha level because that's what's important. And I'm going to start with my alternative hypothesis. And I'm going to remind me that this alternative hypothesis tells me what type of tail test that I have. Because I've got a because I've got a greater than symbol in my alternative hypothesis, I know my test is going to be right-tailed. So it's going to have this region over here to the right. So that's exactly what I'm going to look at. And my rejection region is going to be defined by some value. I'll go ahead and add that value here in black. I'm going to color in that region. I think I chose purple. So let's choose that purple again. So this is my rejection region. And remember, this rejection region is defined by my significance level. My significance level is 1%, so I know the area of my rejection region is 0.01. The question is, how in the world do I find this value that defines that region? And then I'm going to graph my test statistic and determine if it's inside or really to the left or to the right of that tipping point. And that tipping point is going to be the value that defines the rejection region to the right and everything else to the left. Hopefully you remember that to find that value, you're going to have to do the inverse norm. To find the inverse norm, what I've got here is I've got the inverse norm, the area of 0.01, and I need to find, given a mean and a standard deviation of 0 and 1. If you type that into the calculator, you're going to get a negative 2.33 when you round. Now that's not a mistake. That's not a mistake at all, but you should hopefully be saying, okay, there's something wrong with that value, and there is something wrong with it because it's negative. But the calculator didn't do anything wrong. The calculator gave you exactly what you wanted. You asked the calculator, where in the world is there a normal distribution? Where's the area 0.01? Well, really what that's saying is over here on the left, when I've got 0.01 on the left-hand side, this area is defined by a negative 2.33. And that's great, that's helpful, but that's not the value we wanted. We wanted the value to the right of that. So we don't really want the negative 2.33, we want the positive 2.33. And hopefully you can see that that is the same value, and it's because of symmetric in the normal curve. But this formula allows me to think through that. If you wanted to do the other formula, if you wanted to do the inverse norm where there's 99% defined, which is really truly the calculation for this purple region, you can do that. You just have to type in inverse norm of 0.9901, and then you would get it, 0.9901. Go ahead and type that into the calculator, and you'll get exactly what I was saying. You'll get the positive 2.33. So you can do it either way, as long as you understand what you're doing with the calculator. Whatever you tell the calculator to give you, it's going to give you the same thing, or it's going to give you the correct thing. You've got to be smarter than the calculator. So this 2.33 defines that region. The next step we've got to do is just take our test statistic and graph it somewhere on our curve. So my test statistic of 3.37, think about that tipping point of 2.33. 3.37 has got to be to the right, so let's just go ahead and graph it right over here. That's going to be my test statistic. It's kind of hard to read right there. I'll go ahead and draw a nice little arrow here. That's going to be 3.37. So I know that the test statistic falls within that rejection region, so that tells me lots of things. It tells me that I can just do this here with a nice little word here. I can reject the null. Because I'm in the rejection region, I'm going to be able to reject the null. This is not well organized, but hopefully you're getting the point here. And I'm going to continue on to the next type of solving this problem, which is going to be the p-value. So give me just 1 second. Let's just move this guy. Oh yeah, look at that. So now p-value. You start off the p-value. What's cool with the p-value is you start by graphing that test statistic. So I'll go ahead and graph that test statistic. I'll use this yellow because I used it earlier. And the value for that test statistic, remember, is 3.37. 3.37. Now, I talked earlier about the p-value and it being a probability. That's exactly what the p-value is. And what it is it's the probability of this region. It's the area. Remember, probability and area have the same relationship based on this model. So when we talk probability, we're talking about area, and the p-value is truly that red area. That's really what's going on. So we've got to define how we calculate that area. And hopefully you remember we find the calculations of area using another calculation in our formula, in our calculator, which is normal CDF. In this case, it's going to be normal CDF. We're starting at 3.37. and then we're going all the way up to 10,000 or 1,000, 0, 1. You could just put it with those two variables first in the formula. You don't have to add the 0 and 1. But when you type that in, you should get a value of... Yours might be a little off. I got 3.75 times 10 to the negative 4. That tells me it's very, 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 very small, so it's roughly 0. So now the last step, whenever you're doing this second tradition with the p-value, you've got to compare your p-value value versus your alpha value. Remember, you got to compare that to the test statistic. In this case, my test statistic was 0.01. And I'm sorry, my significance level was 0.01, not my test statistic. And my p-value was, as I calculated up there, basically 0, 0.000375, basically 0. In this case, my p-value is low, and when my p-value is low, the hoe must go. So what are we doing in this one too? We are rejecting. That's awesome, that's good. So I've got 2 rejections. I've got the 1 rejection with the traditional, 1 rejection with the p-value, and I can go ahead and step forward with my final conclusion. Now, typing out that final conclusion, remember we've got that keyword from earlier. My keyword was support. So I can use that. And my conclusion showed up right there. There is sufficient evidence to support the claim that the majority of the students thought Math 101 was awesome. I had 2 ways that I rejected the null. It's really important here that you're seeing that I'm rejecting the null, but that does not show up in my conclusion. My conclusion is based off that keyword of support. Remember, I got that keyword because my alternative and my claim matched up. Because of that, I can use that word support. And then because I'm rejecting the null, there I can start off the statement saying there is sufficient evidence. So I'm following along directly from that worksheet. I'll include that at the very end of this clip as I move forward in the next few examples. It's a very important sheet and it'll help you out with these types of problems quite a bit. All right, moving forward. All right, number 3, testing claims about means. I'm going to go through this one a little bit faster. The only difference here is I'm talking about a different statistic. Earlier I was talking proportions, now I'm talking means. In a study of 31 real estate agents, the average income was $85,000. Assume the proportion standard deviation for the income of all real estate agents is 6,700. Test the claim that the population average income for real estate agents is not equal to 81,000. The significance level of 5%. So that's all the information I have. That's all the information I need, and it's all there ready to go. First thing, you should be thinking to yourself, is this a mean or a proportion? And it's not a trick question. It tells you right then and there at the very beginning that this is a mean. The first statement talks about the average income. So that tells you that I've got a mean situation. I went ahead and highlighted those 2 keywords that would tell you that it's a mean. I'm going to go to the next step, which is going to be identifying the claim. In this case, my claim is given to me right there in the problem. It's talking about the claim that the income for the real estate agents is not equal to 81,000. So my claim is going to be that the population mean is not equal to 81,000, 81,000. That's my claim. I'm going to go ahead and go forward to the next step. If that's my claim, my opposite of that claim is going to be if the claim is it's equal to 81,000, then the opposite is going to be mu is not equal to 81,000. I think I got that mixed up, but I think you got it. The claim is not equal to, so the opposite is equal to. The next step is going to be identify those alternative and null hypothesis. Remember, the null hypothesis is always the one with the equal sign. So in this case, my null hypothesis is that mu is equal to 81,000. And then my alternative is going to be that mu is not equal to 81,000. Hopefully you're saying, okay, well, I know what that tells me. When the alternative is not equal to, that tells me several things. It tells me, one, that this is going to be a 2-tailed test. I'm going to be able to miss low and miss high, because right here in the middle is going to be that equal to, the probability that it's equal to. This purple region is all the probability that it's actually equal to. That's what's really happening. This yellow probability is saying that it's less than 8,100, and then the green probability is over here that it's more than 8,100. Both of those, the less than and the more than, both of those miss the mark. What we're really looking for is a probability that it's equal to 8,100, and that's the majority right there in the middle. So that's what we're going to try to prove and talk through. The last thing you should identify and do before you solve these problems is where does your claim show up? And here again, I've got a nice little situation where my claim and my alternative are the same. That's really, really nice because the keyword there that I'm going to use is the keyword of support. And that's going to make things really easy because I will be able to support or not support my claim. Next things I need to do is I need to go ahead and continue on and go through the steps. The next step is to identify the significance level. My alpha in this case, whoa, that's a weird looking alpha. Let's fix that. My alpha in this case was going to be 0.05.
And then the next step is to identify the test statistic. And I know that this is where a lot of you guys get confused. It's really not that bad. You've just got to determine which formula you're going to use for the test statistic. Now, I told you the majority of the time we're only going to use your very often you're going to use the standard deviation of the sample with the formula with the S, because that's what's realistic in real world. In this situation, I've actually been I'm telling you to assume the population standard deviation for the income. I'm telling you that. The population standard deviation, it's no longer the sample standard deviation, it's now the population. So we're going to be using sigma. So that's important here, that this formula is going to be tweaked just a little bit. The numerator doesn't change. It's going to be x bar minus x. I'm sorry, not x bar minus x bar minus mu. It's the sample mean minus population mean over the square root of, in this case, sigma. We're going to multiply that by the square root of n, by n. Now, lots of terms in there. You got to identify what all those are. X bar is just the sample mean, and it's going to tell me right here my sample size of 31 agents, and I got an average income of 8,500. That is my sample mean. So I'm going to go ahead and identify that and start typing and working with that. My sample mean is 8,500. The next thing to identify is my true population mean. I don't know what that is, but I've been given it. Actually, I was not given it. We assumed something. We assumed right here, we're assuming that it's 8,100. Again, that P and Q from the probability, or that mu, it comes from your null hypothesis. So that right there tells me what my value is, so I can just continue with that. My mu is going to be 81,000. And then I've got to come up with my standard deviation and my n. My n is going to be from the population of 31 real estate agents, so I'll add that here. And then my standard deviation is from the sample. It's telling me to come up with the population standard deviation, and it gives me right there that 6,700. So identified everything that I got. Now I just got to plug it into the formula and move forward. I'm going to move myself over here just a little bit so we have a little bit of space. And I'm going to go ahead and solve this really quickly here on the screen. As I was solving this, I noticed that I made a small little mistake. I got too much in proportion mode, and I did a square root here. This should not be square root. In my test statistic, it should be x minus mu divided by sigma, multiplied by the square root of n. My mistake there. Once I've got that fixed, then I should be able to get the correct calculation. I'll go ahead and write out the first step here. That's the first step. I know it may not look exactly like I've written it up there, but I promise you mathematically it's the exact same thing. I did it in that other format just to save room. I'll write the next step here in the same format you're used to. There it is in a format you're probably more used to. Numerator reducing down to 4,000 over 6,700, multiplying by 5.56. When you do end up getting this in the calculator, you're getting a test statistic of 3.32. That's going to help me out tremendously, and I should be able to kind of imply what the solution is right now, but I will go ahead and work through the traditional and p-value models. Traditional method, I'm going to start with my idea of coming up with the rejection region, and then I'm going to plot the test statistic. Rejection region is all based on the alpha value. I've got an alpha value of 0.05, and I've also got an alternative hypothesis of not equal to. So I know there's going to be two-tailed. Remember I talked about that here a second ago. So the cool thing here is I've got two rejection regions, one here on the left-hand side, one on the right-hand side. And the other thing that I know about those rejection regions is I know that when I add those up, I'm going to have a value of 0.05. I'm getting that value from my significance level. So when I add those up, I get 0.05. So I know that each one of them is separate. Each one of them is 0.25 and then 0.25 on the other one as well. 2.5% on the left-hand side and 2.5% on the right-hand side. The next thing I need to do is identify those values that define that region. The tipping point, as one of the students said, that I really like it. That tipping point is going to determine where my test statistic falls and whether I reject it or not. Now, there are a few ways to get this tipping point, but I like to use the inverse norm function on our TI-84s. So if we type in inverse norm, we need to find the inverse norm. We want to find the value whenever you get an area of 0.025. We're going to go ahead and use the normal curve, so that's 0, 1. When you type that into the calculator correctly, you should get a negative 1.96. So I know the one over here on the left-hand side is negative 1.96. There's our left-hand tipping point. Now you should be able to determine that the right-hand tipping point is the same thing, just a mirror image. Because remember, this is a normal curve. Everything is mirrored around. So I can get that 1.96 on the right-hand side. So that's the first step, is to identify the rejection region, and the next step is to take that test statistic that we calculated earlier and plot that onto my traditional method curve. 3.32 is going to be somewhere over here to the right because I know that it's positive. It has to be on the right-hand side. And 3.32 is going to be way over here. So that test statistic of 3.32, that does fall within the rejection region. So I should be able to tell myself right now that I've got a conclusion to reject the null. And that's a really, really good thing because now I can continue on and see if I get the same conclusion with my p-value. So let's see. Looking at the p-value method, the first step is to identify where my test statistic is. So let's go ahead and identify that test statistic. It's going to be falling in the same exact place because it's the same exact test statistic, so 3.32. And in this case, we're trying to determine what the area and the region defined by that p-value, that test statistic is. Now remember, because this is a two-tail test, we've got to also look at the extreme values of negative 3.32. So we've got two regions we could identify. Over here on the left-hand side, this small little purple area, and over here on the right-hand side, this small little purple area. Both of those put together are my p-value. So in this case, it's my p-value divided by 2, which is that region, and then my p-value divided by 2, which is this region over here. This is something we've been doing all the way up to this point. We haven't done it explicitly written out divided by 2, but it'll make sense whenever we start calculating this out. Lots of ways to come up with that area. The way I like to think about it is using our calculator doing normal CDF. And we're going to do normal CDF. We're starting at, I'll go ahead and identify the one on the left hand first. So negative 10,000, comma 3, negative 3.32, 0, comma 1. Let's see what I get. And I ended up getting a value of 4.5 times 10 to the negative 4. That's lots. That's a very, very small number. That's 0.00045. And the good thing about this is if I know that the area over here on the left-hand side is 0.00045, I also know the area to the right-hand side is also 0.00045. If you want to type it in the calculator, you can check, but I promise you those areas are going to be the exact same. So the final step here, whenever I compare my p-value to my alpha level, I've just got to determine what those two were. Remember, my alpha level was 0.05. My p-value is 0.00045 plus 0.00045. That is going to be 0.0009, roughly about 0. The big thing here, you got to identify which one is lower. In this case, my p-value is lower. So when the p-value is low, the null hypothesis must go. So again, I've got another conclusion, and this conclusion does match up with the first conclusion of reject. That's really, really good. Now, I just got to write up my final statement. And there it is. There is sufficient evidence to support the claim that the average income of real estate agents is not equal to 8,100. And you might be thinking, well, how in the world did I get that? Remember, the key word of support comes because my alternative matches my claim, and then I just continue the rest of the framework. I've got that sentence started there for a reason. There is sufficient evidence to support that final conclusion. So hopefully that you've got that down. These types of problems are they're lengthy, but everything should line up and should be good to go.